Mr. Sams, why are we staring at a Cheeto?
Well, because I never ate it last time.
Well, that's good you didn't eat it.
Oh, there's only like 2 calories in it.
Yeah, well, that's true.
Yeah, but then I remembered that we shot the video first, and then we made this lesson, and this has been on
the balance,
directly on the balance,
like lead chloride.
And who knows what else has been on the balance? So that's actually why I'm not eating.
Might cause brain damage if you ate it, or worse.
It's possible. I'm not concerned about the calories really.
Well, I think we should move on to our next topic, Mr. Sams, and that is energy and stoichiometry.
Stoichiometry.
Did you think you were done with stoichiometry?
No.
Yeah. So, hey, we're going to do some stoichiometry stuff today. Hey, one thing we got to do is we're talking about chemical reactions, because
this is chemistry after all.
Yeah, so you have to have a chemical reaction. So here I have a chemical reaction.
Combustion of propane.
The combustion of propane.
One of my personal favorites.
Well, you've got that torch.
I do.
Yeah, and that torch is the combustion of propane.
And I have a barbecue.
Yeah, lots of we all burn propane
turkey
for a lot of things.
fryer.
All right, let's balance this, Mr. Sams.
Okay.
It's not a balanced equation. So
Nope.
remember, it's the Cho-2 rule.
Cho-2.
All right, so I
We
got
do the C's first.
3 carbons, so I'm going to put a 3 there.
And we do the H's.
H's, that'll be a 4 right there.
And we do the O's.
There are 3 times 2 or 6 oxygens here, and 4 here, so that's a total of 10.
Yep.
So this is a big 5. So it's
Okay.
1, 5, 3, 4.
Okay.
But when I understand the chemical now, we're interested in the energy. Well, it turns out delta H, which we learned about a while back, is negative 2,200 kilojoules per mole. So
Negative. That means it's exothermic.
that's exothermic, means it releases energy. I know that because, of course, when I burn propane, like when you burn the torch, it released energy. If I would have touched it, it would have released energy into my hand. That would hurt.
A lot of energy.
So an important thing is that if it's negative, the energy goes on the
right.
product side. So you say plus 2,200 kilojoules. Now you notice something that I didn't do. I didn't say plus negative 2,200.
Right, because the negative just tells you that it's exothermic and therefore a product.
Folks, there's no such thing as a negative energy. That just tells you the direction of energy flow. Yeah. And so this is the equation. Now I want you to think about this equation. The thing that's new about this equation, we're adding the energy component. And as we add the energy quotient, we got 1 mole of this plus 5 moles of this makes 3 moles of carbon dioxide, 4 moles of water, and 2,200 kilojoules. So this is a energy equation, folks, or an equation. And think of the 2,200 as just another coefficient in the balanced equation.
Okay.
Now it's not a nice 1, 2, 3, or 4. It could be 2,200.76. It's just a number.
Right.
Okay. Now let's do one that's a little different.
Okay.
This is the heat of solution of baking soda. If you guys remember back to doing the baggy demo at the very beginning of the year, you had baking soda, you dissolve it in water, and it has an energy. It turns out this one, by the way, it breaks apart into sodium ions and hydrocarbon. I should probably put AQ here as it dissociates into ions, and it has a delta H as well.
That's positive.
Yeah, notice I don't have a negative sign there, so that by definition means it's positive. So we would just say plus 15.9 kilojoules.
Positive meaning endothermic. Endothermic, we put it on the reactant side of the equation.
So if I was going to do some stoichiometry with this, my coefficient for energy is 15.9. For sodium bicarbonate, it's 1. For sodium ions, it's 1. And for bicarbonate ion, it's 1. All right, now let's actually do a problem like we would do on the worksheets, problem sets. Okay, energy and stoichiometry. This is a math problem. So sample problem 1. The value of delta H for the reaction below is such and such. So we have calcium carbonate reacts. All right, now wait a second. We get delta H. It's positive 88. So where's that go?
That goes on the left.
So I'll say 88 kilojoules right here, right?
Yep.
So now I've got some other numbers here.
Oh,
so
okay.
Actually, let's go to the next screen.
5.6 grams, 88 kilojoules.
So this is 88 kilojoules, and we had 5.6 grams of the calcium carbonate. So I've got 5.6 grams of this, and I want to convert
into energy.
This is a little bit different, isn't it? So I'll take 5.6 grams of CaCO3. Start with what you know is fraction number 1.
Convert to moles.
Convert to moles. So I'm going to say grams of CaCO3 to 1 mole of CaCO3. I think that weighs 100.
It's 100, yeah. I wondered if you just knew it off the top of your head.
Yeah, I was pretty sure it was 100. So grams of calcium carbonate cancel. But I don't want grams of calcium carbonate. I want to convert to kilojoules. So here's where we have, this is plus a 1. I'll say 1 mole of calcium carbonate. Now, I put a 1 there because there's a 1 right here from this coefficient. That number goes here. If that number's a 6, I'm going to put a 6 there, or whatever.
Just like a mole ratio
and then
we did.
The 88 is just another coefficient, so 88 kilojoules. It's actually kind of shorter than some of the stoichiometry we've done before. And folks, that's the answer.
Yeah, we get
5.6 divided by 100, and you get what?
4.9.
4.9 kilojoules. So if I had 5.6 grams of calcium carbonate,
it
would absorb 4.9 kilojoules.
Yeah.
Not too tough, is it?
No.
All right, let's do one more example. Let's do one more example, Mr. Sams.
Okay.
So in this example here, we have the combustion of something called heptane. Heptane. Heptathlon. How many? What's a heptathlon?
7.
7 events they have in the Olympics. So, hey, in fact, a friend of mine, he was the coach of the Olympic heptathlon coach.
Oh, yeah?
Fun facts to know and tell. Okay, so, hey, we have this heptane, which is C7H16.
I have a feeling we're going to need a balanced equation.
Plus oxygen. Yeah, that's why I'm starting to write this down. Makes CO2 and H2. I didn't even hardly look at the question, did I, Ms. Shams?
No.
Because I know I need to get balanced equation.
You got to do balanced equation before you can do anything.
All right, the Cho-2 rule. So carbons, I'll put a 7 here. Yeah, okay. And then for hydrogens, I'll put an 8. There'll be for oxygens, there'll be 14 here, plus 8. 8 and 14 is 22, so that makes this an 11, right?
11, yeah.
And that locks this in as a 1. Now, as I recall, we can look back here, the kilojoules for the whole reaction, the delta H is negative 2145. So that goes on the right side.
Yes.
So this is plus 2145 kilojoules.
All right.
Okay, there's my balanced equation. Now, what do I know? I knew I had
1566 kilojoules.
I had 1,566 kilojoules. That's what I had. That's my given amount, and I want to convert to what? I think it was
grams of CO2.
Grams of CO2. So that's my starting point. Okay. Now it's not a big deal, guys. A lot of people get struggle. They say I'm going to start with kilojoules. Yep, that's okay.
Yeah.
1,566
start with
kilojoules.
what you know, always.
And I'm just say kilojoules. There's no kilojoules of something because that's just the energy of energy. If you really want to get particular. Now I'm going to use my coefficient. Now that's a funny coefficient, but that's okay. 2145 kilojoules for every 7 moles of CO2. And then my kilojoules cancel, and now I'm going to just use the molar mass of CO2. So 1 mole of CO2 is equal to so many grams of CO2. I look up at the periodic table, find carbon plus 2 oxygens, and I happen to know this in my head. It's 44. Yeah, a lot of people probably, a lot of you students know that. And so I'm just going to take 1566 times 7 divided by 2145 times 44, and I get
225.
225 grams of CO2. So if I were to produce 1,566 kilojoules, I would also produce 225 grams of CO2. I could also calculate, say, how many grams of heptane would be needed, etc., etc. So a scientist, or an engineer actually probably more likely, if they said, I need so much energy, how many, usually they might actually typically ask this question, how many grams of heptane would I need to burn? Yeah. And they could calculate that amount, and then that's how much they would burn. Typically, actually, they would burn more than that.
Because you never get 100%.
Because you never get 100%, yeah.
Like our Cheeto, we didn't get 100% of that energy in that can.
Yeah, so we doubled it or whatever. So same concept. Okay, great. We'll see you in class, guys, or on the internet. Bye.